Hello everyone. Today we are honored to host Professor Danqi Chen from Princeton University, and she co-leads the Princeton NLP group and focuses on training, adapting, and understanding these large language models to make them more accessible to academia. Really good and genius work. And she had her PhD from Stanford, and her work was earned prestigious award, including Sloan Fellowship and NSF Career Award, Samsung AI Research of the Year Award, and several outstanding awards from ESC and EMNLP communities. And today, Professor will specifically talk about one of the most popular topics around data selection for pre-training and instruction tuning of these large language models. And so please join me in welcoming her in our KUIS AI Talks series. And the stage is yours, Professor. Thank you again.
Thanks for the introduction. Thanks for having me here. So today I'm going to talk about the data aspect of the training large language models. So I'll start this talk with this statement. I believe that data quality is probably currently the most important and also the least transparent aspect in the recent developments of large language models. I'm sure that you all should know that the Llama 3 was out in less than 1 month ago. They haven't really released a paper yet, but they actually put together a blog post about the Llama 3. So if you read their blog post, we don't really know a lot of the details yet, but what they really highlight in the blog post is to train the best language model, the curation of large, high-quality training data is paramount. So we invested heavily in pre-training data. Even for the supervised fine-tuning and the preference optimization part, they also mentioned the quality of the prompts has an outsized influence on the performance of the line models. And some of our biggest improvements in model quality come from the carefully curating this data and performing multiple rounds of quality assurance. So clearly, data is super important. It maybe is actually the secret sauce of a lot of the model developments of in the last few years or so. But as an academic researcher, it's definitely very hard for us to understand all these data curation efforts behind these tech companies, especially the closed source models. But fortunately, there has been also a lot of really exciting open source community efforts in curating open source pre-training data, including, let's say, Red Pajama from Together AI, the DOMA from Allen Institute, and more recently, this FunWeb open pre-training data from Hugging Face, which is actually a replication of the refined web from the Falcon community. And here is actually a figure from the DOMA paper. As you can take a closer look at all this pre-training data, all this data basically like the unlabeled text corpus that are collected from many different sources, including web pages, code data, social media, and the books and the encyclopedia and so on. So it actually really has quite a variety of the different sources, and also the total number, the size, this is DOMA covers. The total number of the tokens in this corpus is already as large as 3 trillion tokens. So this is about pre-training data. On the other side, like the second pipeline, the post-training stage, there also have been lots of the instruction tuning data developed in the last couple of years. So here, the figure I showed here is from the Flank Collection 2022 paper. It's already a little bit outdated than many other more instruction tuning data sets out there. But as you can see that the total number of the instruction data tuning data sets, also the size also has been increased rapidly. And also there has been quite a variety of this kind of instruction tuning examples from the different source distributions, the use cases, and also the quality and the length and so on. So this really leaves us a lot of the fundamental research questions and challenges that we actually need to address. So how should we even measure the quality of the data in the training large language models at both the pre-training and also instruction tuning stage? And how can we actually perform the data selection from all the kind of publicly available data we have? And also, I also want to have this in mind that how to do the data selection efficiently and also effectively is actually a very important thing to consider, considering the scale of the data and also the model sizes. So in this talk, I'm going to discuss 2 lines of research work that have been done in my lab in the past year, in the past couple months. So the first paper I'm going to talk about is called Curating. So here the pronouns are curating, but the Q actually stands for quality. So this is actually a method for selecting high quality data for pre-training. And the second work I'm going to discuss is called LLMs. Is about how to select instruction tuning data for the target instruction tuning setting I'm going to talk about. So these 2 pieces of work were done actually by different groups of students in my lab, and they have very different philosophies. But I really think they also present very interesting and also some kind of like the promising and important directions moving forward to think about how to do the data selection in the training large language models. Okay, so let me directly dive into these 2 papers I'm going to present. So the first paper is called Curating, and the paper was just accepted to ICML 2024. And this paper was, this work was led by my PhD student, Alexander Vetic, and we have released all the models and also the data on this Princeton NLP Curating GitHub repo. Okay, let me talk a bit about the background. So in terms of the data selection for pre-training data, so people all know that how the importance of selecting the pre-training data, but the existing methods for data selection still rely on very simple heuristics, simply because how to do the data selection is actually a very expensive and also challenging task. So some of the common heuristics that people have been using include like C4 rules from the T5 paper in 2020, and also the Gopher rules from the Google DeepMind in 2021. So if you look at this, like the rules that have been used in data selection, they're all rule-based and really written based on some kind of human intuitions, and are written by very simple, like the Python code, as you can see from the screenshot on the right. But these are all like based on some human intuition, very simple, and but they also work well in practice. And there is also another line of work. So for example, this DSIR work from Stanford, which stands for Data Selection with Importance Resampling. So the key idea is to try to resample the data in the pre-training corpus that can minimize the distance between the distribution of the selected data and also handcrafted high quality data such as books or Wikipedia. This works to some extent, but still, like the methods has been actually applied here has been also very simple to some extent. So now let me introduce our work called Curating. So here is a kind of the high-level idea of our approach curating, and like very simple. So our idea is based on this. So instead of using this simple heuristic method for doing the data selection, we select pre-training data with some abstract quality of text that humans can intuitively perceive. The second important insight of this work is we also find that large language models are actually capable of discerning this kind of human intuitive qualities, especially in the pairwise judgments. So I'm going to talk about how this thing works. So this is kind of the high level takeaways of this approach. So let me explain how this curating works. So essentially we have 2 parts. The first part is to figure out how to measure the quality of the pre-training text. The second is how to sample the data according to the qualities that we defined. Okay, so the part 1, the measure quality. So the idea is here is that essentially we try to take a pair of the text, let's say text A and text B, and then we define some kind of abstract quality of text that we actually believe are important. So in this work, we consider 4 different quality criteria, including writing style, educational value, the facts and the trivial, and the required expertise. But I also want to emphasize that I'm going to talk about why we choose these 4 different criteria. But this is actually also a general framework, so we can actually think about many other criteria that could be actually useful for data selection. And after we define these 4 different quality criteria, we use a large language model. In this case, we use the GPT 3.5 turbo model to rank the pair of text A and the text B in terms of each of these quality criteria that we defined. Then we collect these pairwise judgments, like say text A is better than text B or worse than text B in terms of writing style, or let's say required expertise. And then we're going to train a model, a much smaller model. Here we call it curated model on this kind of pairwise judgments. And then we are going to use this model, curated model, to assign the quality ratings to any piece of text that in the pre-training corpus. Okay, so for the second part of this pipeline, we are going to use these quality ratings for the data selection. So essentially, we take the curated model we trained, and then we take like the open data. In this case, we use the Sling Pajama, and we are going to apply the curated model to assign the quality ratings. And then we are going to generate the corpus, which we call it a curated pajama. So essentially, the open pre-training data with curated ratings that the quality ratings that are actually assigned by our curated model. Finally, we have a sampling procedure to select data from this curated pajama corpus according to the quality signals. Finally, we just train our large language models on top of the selected data. Next, I'm going to talk about some kind of design choices in this like a very simple and very intuitive framework. So first is, how should we choose the quality criterion? So we are actually interested in this kind of abstract qualities that are definitely beyond the surface forms. As I mentioned, there's already a lot of like say those surface form matching methods, like the rule-based methods that try to like select the text data with like very simple heuristic. But here we are interested in some more deep and abstract quality of text. So we are interested in the qualities that can be applicable to a wide variety of texts, require deeper understanding of the content of text. And also, this is very important, that we also care about the qualities that can have many subtle gradations in quality. So for any text corpus we are care about, they can actually exhibit quite a wide variety in terms of quality ratings that we care about. Finally, we also want the quality criteria to be actually complementary to each other, instead of like all focusing on one particular aspect. We want to understand like which aspects of text are actually more important for training language models. So let's go through the quality criteria we chose here. So here again, this is one example. So we have one piece of text. I think this is from some piece of news, some news article, and text B is like a kind of code snippet. And we defined 4 different criteria I already mentioned. Let's say writing style. So we have this prompt for the, let's say, large GPT 3.5, which text has a more polished and beautiful writing style. And GPT 3.5 is actually able to tell us that, okay, text A has much better quality writing style. And the second, facts and trivial. So which text contains more facts than trivial? So here we prefer like the more specific facts, obscure trivial, or over some more common sense knowledge, like long tail knowledge. So comparing the text A and text B, clear text A also contains more facts, factual knowledge. And third is educational value. So which text has more educational value, which means that it includes clear explanations, step-by-step reasoning, or questions answers. So we believe this kind of text could actually be better for downstream tasks such as the reasoning task. So in this case, the code text actually has more educational value. That's actually also, there are more and more evidence showing that people have been throwing more and more code data in training the text language models. And the fourth aspect is the required expertise. So which text requires greater expertise and a prerequisite knowledge to understand this text? So in this case, also the text B is definitely harder to understand and needs more experts' knowledge to really understand what is included in this text. So after we define the 4 different quality criteria and the 4 prompts, and then we are going to train the curated model to assign the quality ratings, basically essentially to convert the pairwise judgments to the scalar ratings. So we are going to give the text A and text B like a scalar rating in each of these 4 different criteria. So we actually also have done so in terms of how we decide the quality criteria and also the prompts. So we have done very careful, like the preliminary study and also validation experiments to make sure that read the text that we humans believe there's a clear difference in quality can be also really judged or decided by the large language model. So we did actually construct like 80 pairs of documents that have very clear differences in each of these quality criteria. We found that GPT 3.5 Turbo can achieve very high agreement with human judgments, actually 92 to 99% judgments compared to basically our human selection. And we also find the 4 different quality criteria are only weakly correlated, so the correlation coefficient is also pretty low here. Okay, so next I want to talk about why we actually do the pairwise comparisons instead of, let's say, we can also just letting the large language models to say, okay, how good is this piece of text in terms of writing style or the required expertise? The reason here is we believe that the quality signals should actually capture the subtle gradations in quality. But if we only use the large language models to just give the rating of the individual text directly, let's say if you try the GPT 3.5 Turbo, we find the model can still give us like scores to the different individual piece of text, but most of scores actually really clustered in a very narrow range. So this makes the ranking actually pretty sensitive to the random seed or even the perturbations. However, if we try the GPT-4 instead of GPT 3.5, this kind of the distribution of the scores actually can be distributed much more evenly. But still, like using GPT-4, there's a trade-off here. If we use the GPT-4 to do the annotation, it's actually also much more expensive and costly compared to using GPT 3.5. But if we use the GPT 3.5 for pairwise comparisons, it can do a very good job in telling us which piece of text has this kind of better abstract quality of text. And also intuitively, humans can also find it easier to make pairwise judgments instead of just assigning a score to the individual text. Okay, this is how our the curator model is trained. So basically, we define this different quality criterion. So for each criterion, we collect, so basically randomly sample 250,000 pairwise text pairs from the slim pajama corpus from even actually different subset of the slim pajama. And then we collect 250,000 pairwise judgments from GPT 3.5 Turbo. And then we basically collect this kind of pairwise preference data set, the 250,000 pairwise judgments for each different criterion. And then we basically just need to train a Bradley-Terry model to actually map this kind of pairwise judgment to the scalar ratings. So if you are familiar with like learning from the human preference in the like the instruction tuning state, in the post-training stage of the large language models, actually the formulation is actually very similar. But here we use this Bradley-Terry model to just basically map the pairwise judgment to the scalar rating. So in practice, we essentially fine-tune, take a pre-trained 1.3 billion model and fine-tune the model on the pairwise judgments we collected. And then we produce this curator model for each of these different quality criteria. And we find the fine-tuned model can achieve very high accuracy, actually over 93% of validation accuracy. So that actually indicates that the large language models actually can do a really good job in actually discerning these abstract qualities of text. And then finally, after we obtain this curator model, we use this model to annotate 200, the slim pajama, actually a subset of slim pajama, which has 260 billion tokens. And then we produce this corpus called curated pajama. We actually have a release of all the basically this corpus actually publicly. Okay, so let's take a closer look at this curated pajama corpus. So here we consider different domains of the slim pajama, like Wikipedia, books, Danqi Chen, GitHub, and archive, along these 4 different dimensions. As you can see here, let's say the books actually has a very high quality ratings in terms of the writing style. And the Wikipedia has actually quite some kind of long tail distribution in terms of facts and trivial. which actually pretty much aligned with our expectation. Let's say archive data, it actually has the highest required expertise. So that, but if you look at each single domain, there has been also kind of like the wide range of the ratings across the different criteria. That also means that it's very challenging for us to just select data by simply picking like some single domains. So we have to select documents according to this kind of quality ratings within each single domain. And we also did some really cute like analysis, for example, doing some clustering of the based on some n-gram or unigram features of the text data. Actually, we only use the unigram features. And we find that, okay, the different clusters can also capture very different quality, qualities along the different dimensions. For example, this cluster, which contains like cells or proteins, and this one has a very high ratings on the, like, say, required expertise and educational value. And this cluster has, like, say, contains music and songs. It has much higher good distribution in terms of the writing style, but not so good in terms of educational value and the required expertise. So this is pretty aligned with our human intuition. So this method definitely works. Okay, this is basically how we decided, how we did send the quality ratings to different pre-training tests. So next bigger question is how to do the data selection. So we come up with a very simple solution. Essentially, we try to sample the document without replacement according to different quality ratings. So basically, the probability of the selecting document DI is proportional to the exponential of the quality rating SI in each single dimension, divided by this temperature term. So then this is basically normalized across the entire corpus. So if we think about this like a temperature term, if the temperature term is 0, essentially we are just doing the top case selection. We're just selecting the documents with the highest quality ratings or the lowest quality ratings. But if this temperature is like infinity, essentially we are just basically forced back to the uniform selection. And I will tell you how important this actually temperature term is. It's actually very important to actually balance the quality and also the diversity in terms of data selection. So let me show you the experimental results. So for our experimental results, essentially we take start from this curated pajama, which has 260 billion tokens. And here we just use a fixed domain proportion. So we didn't really investigate how to mix data from different domains. And we are trying to a bunch of different runs by selecting 30 billion tokens out of the 260 billion tokens. And here are the baselines that we are considering. So we are sampling with a curating for each of the quality criteria that we defined. And then we consider the top case sampling, a top case selection. And this kind of sampling with a temperature term of tau equals to 1.0 and tau equals to 2.0. And we also consider baseline control experiments, which is the inverse sampling, that essentially we are trying to sample the lowest rated documents by just using the negation of the quality ratings. And we also consider the mix of the different quality criteria by just select the data from the different, according to different criteria, and finally do the simple merge at the end. And we also consider comparing to the DSIR, the baseline that actually use the books and the English Wikipedia as a reference corpus for the important sampling. And we also compare to the uniform sampling, which is actually a surprisingly really hard baseline to beat and a pretty strong baseline. But we're going to show that using the quality signals can actually significantly outperform all these baselines. And for all the experiments, we did a very clean setup. So we essentially consider training 1.3 billion parameter language models from scratch. And for all the experiments, we consider the perplexity evaluation on the held out set of slim pajama, which is a fixed the proportion domain that sampled from slim pajama. And we also consider downstream task performance, pretty standard downstream task performance using the in-context learning. So here, let me show you the perplexity evaluation first. As you can see here, the red line here indicates the uniform sampling. If we just consider doing the quality of the top case selection, actually the perplexity is pretty bad. So perplexity is basically the lower the better. And if you consider this like the first bar, using the top case selection is actually really bad across the board, across all the different criteria. But if you start to consider the balancing between the quality and the criteria, quality and the diversity by tuning this temperature term, and we found that actually using a temperature term of 2.0 actually works pretty well. So for all the different criteria, it actually outperforms the uniform sampling pretty significantly. Actually, if you look at the perplexity, it's actually very hard to really show the delta in this kind of evaluation because the numbers are already pretty low. But still, comparing the 4 different criteria, the writing style actually gives us the best perplexity result, which is actually pretty interesting and surprising. Okay, next, let's look at the downstream task performance. So here, the y-axis is basically the task performance, the relative improvements compared to the uniform sampling across the 10 different tasks. And the last column is basically the average performance of the 10 tasks. If we consider top case selection, in some cases it helps, but in a lot of cases, it actually doesn't really. Okay, so there's several messages here. So if you consider top case selection, it actually doesn't really help so much across the board. In some, the results are pretty mixed. In some tasks, it helps. In some tasks, it doesn't help. But it really also tells us that the perplexity evaluation doesn't directly transfer to the downstream task performance. But however, if you look at the temperature sampling with the temperature of 2.0, the results actually consistently positive across all the tasks. So if you look at all the tasks here, basically if we try to sample according to all these different criteria, it actually always gives you a better performance, downstream task performance compared to the uniform sampling. And the one interesting thing to look at here is the writing style is actually an exception here. The writing style, which gives us the best perplexity result, actually gives us the worst average performance in terms of downstream task. So this is actually very interesting thing about. But the fact the required expertise, the blue bars here, and also the educational value actually gives us pretty consistent and really impressive improvements across all the tasks. Okay, so let me just summarize this work. First, I also didn't get a chance to talk about this work so we basically propose this general framework for data selection according to this kind of human perceived quality ratings. But in the paper, we also show that the quality ratings can be also used to adjust the order of the data points, can be used in constructing the curriculum for training the data. That means that instead of doing the data selection, we can, if we just fix the data by just changing the order of the data points according to this kind of quality ratings, this could still make a positive impact. And this, we actually think this is actually a pretty promising direction for the future investigation. And given all the data selection methods could have already encoded some kind of certain societal biases that is inherent in this data selection. So in the paper, we actually have already started some kind of certain known social biases in the data selection methods that we proposed. But we believe that this is actually also a very important venue for study the social biases in all the possible data selection methods. And I deeply believe that using the model-based quality signals will be actually a very important direction moving forward. And there will be a lot to think about in terms of the criterion and also the how to leverage models to actually assign the quality signals for data selection. Finally, there are a lot of work we can still do here in terms of more fine-grained data selection, including how can we actually propose better ways to combine the different quality criteria. So in this work, we only consider just simply merging the data selected from the 4 different quality criteria, but there could be more sophisticated ways, more principled ways of doing this for combining the different criteria and also as well as increasing the diversity. And we also believe that we can actually perform some more fine-grained annotations. For example, the data that actually requires different types of reasoning, we can use a stronger model, let's say GP4, to annotate the different skills or the different types of reasoning for the data curation. And also, finally, another really exciting research venue is how to combine this kind of the largely public available pre-training data and the synthetic data in the pre-training process. At the end, I also, just of this part, I also want to mention that even the Llama 3 blog post says that has such a sentence. We don't know any details here, but they found that the previous generations of Llama actually pretty good at identifying the high quality data. So even the Llama 3 pipeline, they chose to use Llama 2 to generate the training data, to train the text quality classifier to actually select the better data. So I'm sure that this idea will be picked up, and also there'll be also more work in this space actually in the coming months or years. I want to mention our work has been already done like for 6 months. So the Llama 3 paper, actually they just released the work like 1 month ago. So there's definitely a lot of exciting things going on in these directions. Okay, so this basically all I want to tell you about this part. I can pause a bit and see if there are any questions before I move on to my second part. Yeah.
So maybe I can ask a quick question. So here, in order to train your ranker to rank the quality of the documents, we are just using a single language model, GPT 3.5. Would that make sense to look at the ranking scores of some other language models, and maybe like each of these models might be somehow assessing a different aspect of the data, so that maybe that could further improve the quality of your auto-generated labels?
Yeah, definitely. That's an interesting question. So we haven't done this in this work, but I do view this as a like a kind of future direction for further exploration. Yeah, the key message in this work is that yeah, we want to define some kind of human intuitive abstract quality criteria, and then we show that GPT 3.5 is able to do this. But I believe that collecting a bunch of the different models and from different sources and the weak models, stronger models could actually and how to ensemble these judgments could be actually really interesting to explore. Actually, recently there has been some work trying to use like an ensemble of the different models for as judgments, LLM judge, to actually replace one single LLM judge. So I would say that's definitely promising. But also we need to think about the cost. So there is always a trade-off between the cost and the quality. Yes.
Thank you.
Any other questions? Okay, then I can move on to my second part. Okay, so in the second work, I would like to talk about another very different style, different approach called LESS. Here, the idea is to actually use some kind of gradient information, some influence estimate to select the instruction tuning data for setting we call the target instruction tuning. So this work was led by 2 PhD students at Princeton, Mengzhou Xia and Satika Malady, and also collaborated with Sachin from University of Washington and my colleague Sanjay Arora from Princeton University. So in the last part, I talked about the pre-training. So in this part, I'm going to focus on the instruction tuning. So let me start with why we care about instruction tuning, data selection for instruction tuning. So there is a very nice paper, this paper called Tulu from University of Washington last year. So they basically try to investigate. They start with a vanilla Llama 13 billion model. They found there actually has been a like great variety of the different instruction tuning data. So they try to throw in the different subsets of the instruction tuning data, like one by one, and also evaluate on the different evaluation benchmarks, including, let's say, reasoning, factuality, multilinguality, coding, and also open-ended generation. So the takeaway from this work is, if we just combine all the instruction tuning data sets, So fine-tuning process could become very expensive because the total amount of data for instruction tuning could be pretty big. And also the combining all the instruction tuning data sets doesn't always work the best. So on average is probably the best. But if you look at individual columns, for example, this column, let's say this number for the coding task is only 25 if you combine all the data here. But if you only look at some subsets, so the numbers could be as high as, let's say, 36.6. So combining all the data sets, the instruction tuning data set, doesn't always work the best. And there is another work, a pretty highly influential work called Lemma, less is more for alignment. So this paper from Meta last year, they proposed a hypothesis that they basically claim that the knowledge in the large language models has been already acquired during the pre-training stage. And the instruction tuning essentially only teaches model which subset or which sub-distribution of formats to use after fine-tuning. So they claim that the quality and diversity really matter to the final model quality. And in this work, they've essentially just manually curated 1,000 instruction tuning data sets for fine-tuning. And it actually works pretty well compared to like the prior work that actually relies on a lot of the many more instruction tuning examples. So this work, they did like a manual selection of 1,000 instruction tuning examples. But this work also inspired a lot of follow-up work on how to do the automatic selection of the instruction tuning examples. So in this work, so we actually focus on a slightly different setting. We call it target instruction tuning. What does that mean? So basically, the research question here is that we have one particular target application in mind. So for this particular application, we actually have like several examples, only a few examples of this target application. And our goal is to select relevant instruction tuning examples for fine-tuning. And our goal is to figure out how to select the instruction examples for this downstream task in an efficient and also effective manner. So why do we care about a few examples? The reason is very simple. So because for a lot of downstream tasks, people don't want to annotate a lot of data. There will be very little data exists for target applications. So in this case, this is basically also the motivation for in-context learning. So in this paper, we essentially only use very few examples that people only used in the in-context learning setting, that people use the examples that put in the context for fine-tuning. So we also only use a few examples of those examples for the for selecting the instruction examples for instruction tuning. And also, why do we care about this target instruction tuning? It's because if we only use a few examples to select the data for instruction tuning, this can actually achieve better performance than just a general purpose model. Let's say the Lemma is a kind of more general purpose model. But here, if we try to curate the data for the specific downstream task, it can actually give you a better performance. So I'll give you a little bit sense of what this task really looks like. Let's say if we have a downstream task, like a downstream application, which requires doing some kind of performing some kind of form of the logical deduction. So this is one example of logic deduction example from BBH. Essentially here, you don't have to read the example. Essentially, there are kind of three choices here. And these three choices basically tell you that, okay, the A is better than B, and the B is better than C. Then the model is trying to ask like, which is actually the worst or which is actually the lowest. And there are a bunch of the different instruction examples here. There's a lot of different instruction examples here. So the example on the upper right part of this slide is a question answering example from like a data set called Dolly. And the bottom right here is the example that actually focuses on the geometric reasoning from the FLAN collection data. So the question is, which of this instruction tuning example actually helps me most on this particular downstream application? If you just look at the text here, it's actually very hard to figure out which example is actually better just based on some kind of surface form features. So this is how actually our approach works. So in this paper, we present this approach called LESS. So here are some kind of key messages of this approach. Essentially, we are the first to propose to use this kind of inference formulation to estimate how the training examples in the instruction tuning can influence the model predictions or the validation examples. And we are going to do this kind of inference estimate and use this as a proxy score for data selection. And we adapt the inference formulation from prior work for, let's say, detecting mislabeled classification. But we also make it work for the add-on optimizer and also the sequence level instruction data selection. And also very important thing is we also did a lot of the approximations to make this algorithm actually very efficient. So this is actually very important considering the scale of the data and also the model sizes. How to make this algorithm actually really practically feasible is actually a really important angle of such a method. I'm going to tell you how we did this in a few slides. Okay, so what do I mean by the training influence or how to estimate this influence estimate? So basically the idea here is we want to select the training data to maximize the validation loss on some particular examples in the validation set. So let's think about we'll consider one validation example Z from the validation set. And the loss of on this validation example Z changes after one single iteration step during the training can be better written in this way by using the first order approximation. So the loss of the loss on this data point Z at the time point t plus 1 minus of the loss on the data point Z at the time point t can be approximated as a gradient of the theta t with respect to Z and also the weight difference, the difference between theta t plus 1 minus theta t. And if you consider doing like a SGD step on one training example X with, let's say, with a constant learning rate eta here, so we can basically write the difference of the loss as the inner product between the gradient of the theta t with respect to X and the gradient of theta t with respect to Z. And finally, if we want to define how important this training example X actually can reduce the loss on the validation sample Z, essentially to maximize the loss decrease. Essentially, we just need to try to find the training example X to maximize the inner product between these two gradient vectors. So we actually adapt this formulation from this paper in NeurIPS 2020 called Estimating Training Data Influence by Tracing Gradient Descent. But this paper uses this formulation to identify mislabeled training data, but we use this formulation to design a data selection strategy. Since we need to train the models over multiple epochs, so let's say assume that we need to train the data over n epochs, and then we want to choose the training data X to aggregate the influence of the data point X over the course of training. Essentially, we try to choose the training data X to maximize aggregated influence by summing up this inner product of the gradient information, different checkpoint theta I with respect to X and the theta I with respect to Z, and then we aggregate this inner product multiplied by the learning rate at a different epochs. So this is basically the idea of using the training influence for data selection, and we are basically adapt this formulation for data selection. But as I mentioned, directly adapting this for the instruction tuning setting is not that straightforward. There are two challenges here. The first challenge here is for instruction tuning, people do not use SGD formulation. People actually use the add-on optimizer. So in this work, we developed the formulation of this influence estimate for add-on instead of SGD. So I'm actually not going to do the math part, but essentially we can write things in a very similar way, but by writing the influence of the data training example X on the validation example Z as the dot product between this gradient term and also this gamma term of the theta according to the theta t on the training example X. And this gamma term is essentially basically can be written as this kind of the first order moment and the second order moment M and V in the add and updates. So in practice, this can be actually is actually not feasible to calculate. So the one key insight we did in this paper is this is actually a feasible solution, but also efficient solution, is that we actually propose to use some kind of warm-up training. So essentially, we only use a tiny fraction of the data. In the experiment, we only use 5% of the training data to do the warm-up training. And then we just save all the checkpoints, theta t, after every single epoch. And then we can estimate this M term and V term. And then finally use the M term and the V term to estimate this gamma term. Finally, we can just use this formulation to actually select the data for training examples X to maximize this inner product between the gradient and the gamma terms. And another complication of the adapting this inference estimate to the instruction tuning is that the selecting instruction to data is actually a task at a sequence level. But all the instruction tuning data, their gradients essentially the average of the token level gradients. And all the sequences actually have the variable length of sequences, a variable length of tokens. So in the paper, we found that, so ideally, if we really want to adapt this inference estimate, we should do the token level data selection. But this could be actually become really expensive in practice. So to actually, in order to account this and to do a better job in the sequence level selection, we actually, in practice, we consider using the cosine similarity instead of the dot product to estimate this influence. So this is basically our final formulation. So essentially, we try to aggregate the influence over the n epochs by calculating the dot product between this gradient term and the gamma term, and apply this cosine similarity, and multiplied by the learning rate, average learning rate over at every single epoch. Choosing the cosine similarity instead of dot product because we find that if you use the dot product, the gradient alone would be actually anti-correlated with the length of the combination. But using the cosine similarity would actually mitigate this problem, and this would also work well in practice. Okay, so these two slides are probably the most messy slides I have, but this is basically the kind of high-level idea we did by using this kind of influence estimate for data selection, and we also make it work for add-in and also instruction tuning data. But still, we are not done yet. But just using this like a formulation for data selection is still very expensive because the models are very large. The total number of examples we have for instruction tuning is also very expensive. So we have to do a lot of efficient approximation to make this really work. So here is actually the kind of the outline of the final algorithm, and see how we actually do make it practical. So the method essentially has 4 steps. So in the first step, as I said, we did some kind of warm-up training. So essentially, we just take like 5% of the training data to train on the 5% of all the instruction tuning data to get all the checkpoints after every single epoch, and then we can collect the first order and second order moment terms MI and VI after every single epoch. But one important design choice here is that we actually chose to use LoRa instead of the full parameter tuning, because the LoRa, if you use LoRa adapter tuning, we can actually reduce the gradient features to actually only less than 2% of the number of parameters. So this will be actually greatly reduce basically the gradient features we can use for data selection. And for the second step, so after we calculate all the kind of LoRa features after every single epoch, and we further try to reduce the dimension of these gradient features by doing some kind of random projection. So at the end, we only actually do this random projection of the LoRa gradient to reduce to only a dimension of 8,192. So in ablation study, we show that if you can do the random projection to even, let's say, 1,000 dimension, the method still works pretty well. So after we calculate all these kind of gradient features, the gamma terms, we can just store all the gradient features in a data store. And this gradient data store can be reused by doing the data selection for the different downstream tasks. So this is actually very important. So we just need to do this kind of gradient calculation only once, and then we can actually reuse the data store many times for different applications. And the third step is the data selection. This step is actually very cheap. So basically, we just use the added inference I just talked about to compute the inference and select the data that can maximize the inference on the validation set that we care about. So after we calculate the gradient data store, the gamma terms, for every single downstream task, we just need to calculate basically the gradient term of the different checkpoint with respect to the validation example, and then we calculate this added inference, and then we use this as a proxy for data selection. And this can be very cheap because the data store has been already computed and stored. And by doing the random projection, the data store could actually doesn't require a lot of the storage. It can be pretty cheap to store locally or on the disk. Finally, after we do the data selection, we just need to train the model on the data we selected, and finally we can deliver this instruction to the models. So let me show you how well this method actually performs. So here are the experiment settings. So we consider, so this is not particularly large, but we can easily extend this experiment to much larger setting. So we consider instruction tuning setting, a data set from the different sources, including the FLAM v2 and the chain of thought data and the Dolly data set and the open assistant. So this instruction tuning data sets actually really have very different properties and come from very different source distributions. So that's good that we can actually, even for each of these like FLAM and the chain of thought, they also come from the basic combination of the many different sources of the instruction tuning examples. And for the evaluation, we consider the several very standard evaluation, including MMOU, and the TIDA QA, which is a multilingual question answering, and also the BBH task, which consists of 27 reasoning tasks. And for the models, we consider 3 types of models: the Llama 2 7 billion model, Llama 2 13 billion model, Mistral 7 billion model. So we chose 3 types of models. First, we want to show how general this approach can be applied to the different types of models. The second is actually more exciting, is we show that the data selection that can be performed based on different models can be actually transferred and shared across the different models, even across the different model families. So this is actually really interesting. So let me show you the many experimental results here. So on the left is basically the results of the training Mistral model. On the red bar here is the training on the full data sets. We have all the instruction tuning data. And the blue bars here, we consider we only choose to basically only train on the 5% of the selection data. So here is a Mistral data, a Mistral model. And on the right, we basically train the Llama 2 13 billion on the 5% data. As you can see here, so the second bar here is basically only fine-tune the 5% randomly chosen data. So it actually doesn't work so well. But if you consider using the influence estimate using our approach less, and by only using 5% data, it can actually outperform the performance using 100% of the instruction tuning data. And another interesting finding here is the third bar here. Essentially, we just use the Llama 2 7 billion model for data selection, and then we train the Mistral model and the Llama 2 13 billion model on the data selected by Llama 2 7 billion model. And we find that this also works really well. So that means that data selected using the smaller models or the models from even different families can actually transfer pretty well. So this actually has some pretty good implications in terms of efficiency. So we can actually build the data store using the smaller model and then train the larger models on the data store that built by the smaller model. And we also conduct an extensive comparison with other data selection models, including, let's say, the n-gram features such as BM25, and this like a important resampling method from Stanford. And we also consider 5% data selected by some kind of models, hidden representations, basically some kind of semantic representations of features for data selection. And the less outperforms all the other approaches that based on the surface form features. And here's actually a really interesting example I want to show you here. So let's say if there's a validation example here, that is a question answering example in the language called Bengali. And if we consider using the BM25 or using the repetition-based method for data selection, these methods all chose some kind of instruction tuning examples in the Bengali languages. But only our LLMs approach is able to choose a question answering examples that actually in a different language, in the English language. So essentially it shows that it can actually choose a question answering example in the different language that can actually help us transfer to a question answering example in the Bengali example in the validation example, the validation task. Okay, so let me summarize this part. So in the paper, we also have a lot of ablation studies showing that this warm-up stage will be actually important, but it can be done actually very cheap way. And the more checkpoints we can use for inference estimates, actually we can achieve better performance. We also show that smaller dimension projection, such as 1024, can be actually sufficient to deliver very strong performance. But there are also still a lot of limitations and the future work we can explore in this work. For example, if we use the warm-up training to estimate inference, it's still essentially just approximation. So how close is the approximation, and can we do better to approximate this better? It's still an open question. And we also, essentially in the data selection, we try to minimize the cross-entropy loss. But this doesn't always transfer to the better performance in downstream tasks. How can we actually directly do the data selection for the final downstream task is actually an interesting question. Finally, using this kind of gradient-based data store for retrieval is actually a very interesting thing to think about, because most of the retrieval methods have been actually relying on some kind of surface form features and also some embedding features. Okay, so this is basically all I want to tell you today about the work. So this is basically my last slide. Let me just finish this, and I will see if people have any questions about my second work. So currently, I think it's actually really exciting time that we have seen a lot of the explosion of the data sets at the different stages of training large language models, including pre-training, supervised fine-tuning, and also preference optimization. And personally, I believe that data is actually arguably it's probably more important than architectures and learning algorithms. And I think there's still a big room and a lot of open research questions to think about how to do the data selection and the quality filtering. But a common thing today I want to talk about is actually the efficiency, because how to do the data selection in the era of the large language models. So really the key challenges is actually the efficiency, because the data model size is so large. And also we have so many data sets that we can actually use for data selection. So how can we design both efficient and effective method for data selection is really the key. And I still believe that currently most of practice in the developing large language models are pretty heuristic based and very ad hoc. So we actually really need to advocate for more systematic and principled ways of doing the data-centric research. But still, there are a lot of challenging questions, including, like, say, the compute. This experiment is still pretty compute expensive. And if we consider doing these experiments at a smaller scale, whether the smaller model, the smaller data sets can actually transfer to the larger models or larger data sets. These are all the open questions and challenges we need to answer in the next few years. Okay, so I'm just going to stop here, and thanks for joining me, and I'm happy to take more questions.